Hi, and welcome to week 14. Wow, the final week. Where did the time go? I know. Try to hold back the tears, okay? Well, look, here's a fantastic photo of a place several of you in class visited last summer with me when we went to Hawaii. This is the famous green sand beach on the south coast of the Big Island. What's happening here is there's a large littoral cone, and for those of you that don't know that term, it's basically when a magma erupts near the ocean, it interacts with seawater and creates an even more explosive an eruption than it would have been. So instead of getting a cinder cone, you get more ash. Pretty prominent around the coastlines of Hawaii and the Galapagos. Well, anyway, this is a younger cone. You can see the bedded nature of it here. And inside, this lava that erupted had a very high proportion of olivine. So as the cone gets eroded by the ocean, the olivine is very resistant to erosion for the features or for the reasons we'll talk about, but mostly no cleavage, high density, good strength, high hardness. So basically what happens is you beat up the cone and the olivine is what's left over. So the beach here is, that green color is not manufactured, that's for real, and you end up with a green sand beach. And this is a place that we hiked to one of the days of our Hawaii field trip, and of course the water's fantastic, the beach is fantastic, and you know, it's just fun all over. Some humans down there for scale. Well, olivine, of course, is one of the best Nesosilicates, one of my favorite minerals, because I spent a long time working on basalts. It's easy to identify, it's unique, it's just a great mineral all around. Well, here again, it's just like, it's not that you would have forgotten, right? But all of the minerals we have spoken about that have formulas that you will be responsible for, and the ones from last week. Look at that hornblende down there. What a garbage can. And you'll remember that those parentheses are indicating the various structural sites that can hold cations. And so it looks a little mixed up there with all the S's and M's and CA's and stuff, but not every mineral has all of the cations. But hornblende, as we found out last week, has a lot of places to put stuff, so therefore its composition can range widely. Well, this week we're going to review the general attributes of the final mineral group we'll be talking about, the Nesosilicates. And there is one more silicate group that we won't be talking about. That's the sorosilicates. They're the chain ones. And a good example of a sorosilicate would be epidote. But we only have so much time with this format, and so it is what it is. And I know that you've learned how to use the microscope. Your mineral ID skills are getting good in lab, both in the microscope and in hand specimen. And of course, you know, you were never meant to see every mineral, but you've seen many of the most common minerals, the rock-forming minerals. And of course, should something new cross your path, you know, you've got the skills to figure it out. Okay, so anyway, we're going to review the general attributes of the Nesosilicates. We're going to discuss the common physical properties, the properties that are shared by all Nesosilicates. We'll document the optical and physical properties of the common Nesosilicates and discuss their occurrences. Well, here's a short list of the very common Nesosilicates, and you can see that right up here at the top is olivine. And for those of you that don't know, olivine has two end members, the forsterite end member, which is the magnesium-rich end member, and then the phthalite end member, which is an iron-rich end member. And olivine is a solid solution series, like we talked about with plagioclase, and it can range in composition from magnesium-rich to iron-rich. So then there's the garnet group. And again, everybody loves garnets because they're easy to identify. They're very classically, they like to grow into those dodecahedrons. They're hard. They don't have much cleavage. And under the microscope, they're fantastic because they are isotropic. So you'll see a lot of garnets when you guys move on and talk about metamorphic petrology. Zircons are in this group, the oldest living things on Earth. Well, not really living, but the oldest things on Earth, right? They outlived the oldest rock. So how can they be older than rocks? Well, the rocks that grew with these zircons in them are long gone, but the crystals are left over. And let's see. A group of minerals that most people have not heard of up to this point, but will be very popular, again, in metamorphic rocks, are the what's called the aluminosilicates. That's silica with aluminum, and this is andesite, andalusite, sillimanite, and kyanite. Then topaz, which most people have heard of because it's the 8th mineral in the Mohs hardness scale. Yeah, and then starlight. Okay. Well, Neso means island, and another word for the nesosilicates are orthosilicates. But in the nesosilicates, the reason that prefix was used was each individual tetrahedra is not touching or bonded to another tetrahedra. So each silicon atom only sees those 4 oxygens, and each one of those oxygens only sees the 1 silicon. So you'll remember back I gave you a problem set to do talking about Pauling's rules, and one of the questions I asked you was to kind of sort out what was going on with olivine, and when you did the little maneuvers there, you came to find out that you know, each one of those oxygens only saw 1 silicon, meaning that they can't be bonded to other tetrahedra, and that's certainly the case. So these tetrahedra are ultimately stuck together via ionic bonds with these interstitial cations, and in this diagram, the green and the red are representing iron and magnesium, both +2s. Because remember, the SiO4 is a -4 overall, so we got to get 2 cations to bond with it to even it out. And in olivine, this is the structure of olivine, and you know, you gotta have you know, at least 2 magnesiums or 2 irons or a mixture of the 2, which is why it's got that kind of Christmassy look to it with the red and the green. Now, some of these tetrahedra are pointing up, some of them are pointing down, and I included over here another graphic to kind of show you how this all works in 3-dimensional space. And this would represent, if you remember the term, a unit cell. This would represent 1 unit cell of olivine. And remember, the shape of the unit cell is what gave us the crystal systems, right? That's orthorhombic, so it's got that shoebox shaped unit cell. And with the silica tetrahedra and the cations that stick everything together. Pretty cool. All right, so anyway, that is what nesosilicates are all about. The tetrahedra do not link up with corners, edges, faces, nothing. Now, I wanted to mention something that I would talk about in intro, and that is, if we go back and we take a look now, you've been exposed to all the various silica tetrahedra and classes. So we started talking about the framework silicates, right? These were the quartz and feldspar. And of course, in that case, every tetrahedra, the corners are all bonded to other tetrahedra, giving you this large framework silicate. And then we talked about the sheet silicates. We did not, this is a ring, we didn't talk about the rings. That's the sorosilicates. But we did talk about sheets, we talked about chains, both single and double. And then here, this time, we're talking about isolated tetrahedra. And what I wanted to kind of point out to you, and this is more of a petrology thing, but it's hard for me to divorce mineralogy from petrology, is think about growing mineral structures. Think about trying to grow a mineral in a magma. So when you have a magma that's cooling down, the higher the temperature, the harder it is for these crystals, right, to form, because the tetrahedra don't want to link up. You know, temperature is vibration. And what I'd like you to think about is that think about that temperature as sort of a thermodynamic wind. So I've got my symbol of wind over here, and imagine that our silica, you know, these polymers that are trying to grow, think of them like, oh, I don't know, let's say you were trying to build a stack of cards, or maybe some sort of model using little, you know, balls and spokes or something, you know. But anyway, well, no matter what you're building, can you imagine trying to like a tent or something like that, and imagine that the wind is blowing. Which one of these structures is going to be able to stand up to the highest wind? And so really, in an analogy, you've got a crystal growing in a magma, and that vibration, that heat, right, the temperature, not so much heat, but temperature is trying to rip apart, right? It's shaking, it's vibrating, these atoms are vibrating, and it's trying to tear apart your structure. So which one of these would withstand the highest degree of vibration? And of course, it would be this simple structure, right? This nice little isolated tetrahedra. You know, those would withstand this sort of thermodynamic wind the best. And of course, what would happen on the other end is the most complex structure would be something that couldn't form until the wind died down. So at the coolest temperatures. Yeah? So when you think about next semester, when you think about trying to grow minerals in a magma, you know, think about it that way. So when we look at Bowen's reaction series and you think, well, here's olivine, you know, forming at the highest temperatures, it's also got the most simple structure. And then when you get down here to the bottom of the list, right, quartz, you know, you've got the most elaborate structure. So, you know, and it doesn't work perfectly in every case because there's different, you know, thermodynamic considerations. But, you know, when you think about pyroxenes, even, right, the single chains form before the double chains, and then you get down here into the sheet silicates, which are more complex than that. So anyway, that gives you a kind of a good handle on if somebody ever asked, you know, you've always been told olivine forms first in a cooling magma. Well, why? Well, this answers that question. Also, you'll be thinking about things like, well, when a rock starts to melt, what are the materials with the lowest melting points? Well, they're down here, right? They're the ones that have the most complex structures, and things can be torn apart easier at those colder temperatures. So, hottest temperatures, simplest structure. All right, something simple, right? So when you go home for Christmas and your mom asks you what you've been learning, see, you can tell her something cool. All right, so let's talk about some general nesosilicate attributes. Well, there's a very dense, tends to be a very dense packing of atoms, which leads to a high density and therefore a specific gravity. That's really the same thing. And also, this dense packing of atoms tends to create minerals with a high degree of hardness. So when I look at some of the common nesosilicates, olivine, garnet, zircon, sphene, and kyanite, look at their specific gravities, right? The average specific gravity of like quartz is around 2.7, 2.8. Well, here's 3.2 to 4.4. Of course, there's a range because olivine has a very wide range of compositions. Well, not very, but it ranges from magnesium-rich to iron-rich. Look at garnet here, 3.5 to 4.3. And you can see zircon, very dense mineral, 4.67, so almost doubling the density of something like quartz, right? It makes them sink, it makes them fall out of solution, it makes them fall settle in a magma. Let's see, what else? Hardnesses. Look, all of these minerals have hardnesses, 6. Here's sphene is a little softer in kyanite, but look at the hardnesses here, 7.5, 6 to 7.5, 6.5 to 7. And then when we look over here, something that you now can appreciate, which is along with that higher density comes higher refractive indices. And this is going to make light bend more, right? So, you know, we don't even have oils this high for you to sample these sorts of things or to try to identify them, right? Because of those oils are too dense. So we have densities that range up to over 2, which is going to slow light down. That means that light is slowing down over, you know, twice as much as it would go through a vacuum. And that bending is going to create an important aspect is that well, it's all due to this sort of these nesosilicates have these equidimensional packing. So our crystals are going to tend to be compact. They're not going to tend to be real long and narrow like what we saw in the pyroxenes. Yeah, and because everything is sort of packed in there equally, we don't tend to see a lot of cleavage in these minerals. Now again, some do, some have good cleavage, but overall we're talking about nesosilicates as a group. We're going to tend to see densely packed, equidimensional, high degrees of specific gravity, density, and hardness. Now, because of that high density and the high refractive indices, and the lack of cleavage, and they're hard, right, we're going to be able to polish these suckers, and it's going to really make the light refract, which is what you want in a good gemstone, right? So, topaz, zircon, you guys have all heard of, you know, cubic zirconia, right? Kind of a diamond substitute. Peridot, that's olivine, right? And then garnets. So this group probably has a better supply of gem making materials, right, than other groups. Okay, so talking about the specific groups. Now I'll talk the most about olivine, and then as we go, it'll get less and less. You know, olivine is a very common mineral, especially in mafic and ultramafic rocks. I've showed you before that the mantle is composed of, you know, a lot of olivine, and therefore rocks that come out of the mantle like basalt are going to have olivine growing in them. And the formula for olivine is Mg, Fe, meaning you can have all Mg, or you can have all Fe, or you can have a range of the two. And there's 2 of those, right? And those are plus 2s, so they balance the SiO4. And the range is the magnesium-rich version, so it's Mg2 SiO4 is forsterite, Fe2 SiO4 is phaolite. And over here we can see pure forsterite, FO, and pure phaolite, Fa. And these are a solid solution series, meaning that there isn't one exact composition, that you can vary the amount of Mg and Fe over this range, just like we did with the plagioclase feldspars. Now, when you see olivine's compositions being spoken about, it will always be in the percent of forsterite component. So they'll say, what is the weight percent of FO? Or they'll say, if it's FO 100, FO 100 is forsterite. That means it's all magnesium. If it's FO 80, it means it has 80% magnesium and 20% iron. If it's FO 20, it means that it's 80% iron and only 20% magnesium. Just like we talked about AN content being the calcium-rich version of plagioclase. It's just by convention. So when you're reading a paper or you're talking about basalts and olivine compositions, you're going to see people talking about the FO content. And I don't want you to be confused. This is a phase diagram showing, based on the composition of the olivines and your magma, what will crystallize and when the magma cools down. A very, very common phase diagram that you'll see in petrology. And what all this means is if you have pure forsterite, no iron in the mineral at all, it melts at 1890 degrees Celsius. That is flippin' hot, right? So pure olivine in the mantle will not melt until it got to be 1890 degrees. Pure phthalate component, meaning all iron olivine, melts at 1205 degrees Celsius. And as we vary the amount of magnesium and iron, you can see this upper curve tells you the temperature that that magma will melt at, ranging from 1890 down to 1200. But it's more than just that. So if we took a composition of a magma that started at A, so that would be somewhere around FO58. If that magma was at 1800 degrees or 1850, it would still be in the liquid field, right? It would make its first crystal. It would begin to crystallize its first olivine crystal at 1700 degrees, and the composition of that olivine crystal would be about FO80. And this is really cool because you have an FO58 composition magma, but the very first crystal it makes is of composition FO80. And man, when you start to understand this stuff, that makes petrology really fun. And it also tells us that this magma will be fully crystallized at just a little bit under 1500 degrees. And I'm not going to describe this much more because you will get this in petrology, but it's really neat and it explains a lot about how things work. We can think about either heating up rocks and melting them, or we can think about cooling down magmas and crystallizing them. Okay, but that's a classic solid solution phase diagram. And this one, of course, is for olivine. Okay, so the hardness of olivine, very hard, 6.5 to 7, almost up there with quartz, between quartz and the feldspars. No real cleavage. They'll tell you that it's got like a super poor cleavage. Now, if you have really poor cleavage, it's like you have a fracture, meaning it'll break kind of along a direction, but it ain't great. Okay? So that's the way that works. So olivine really does not have great cleavage, but it does have okay fracture. Well, you'll see when I show you a picture, they're always cracked looking. The magnesium-rich versions are the green color you have come to know. The iron-rich versions are very yellow. Now, olivine comes in a granular form. You don't see real big crystals when it comes in peridotite. So this is a mantle xenolith. I talked about these last week. There is a big chunk of peridotite rock, right, that was hauled to the surface in a magma that erupted. Here is a chunk of also peridotite, but this one contains nothing but olivine. Okay, and you can see it kind of looks like sugar crystals in there. They're not. It's not one big chunk. It's a bunch of little sort of sugary grains. Here as well, the crystal size is just a little bit larger. Here, the black that's mixed in here, right? We talked about this last week. Those are pyroxenes, right? And whether they're clinopyroxenes or orthopyroxenes, you would have to look closer. But in this sample, I know that these are orthopyroxenes. So look. This is a classification diagram for ultramafic rocks, rocks that contain all pyroxenes or olivine. There's olivine, there's orthopyroxene, there's clinopyroxene at the corners. So if you contain greater than 50% olivine, you're a peridotite. If you contain less than 50% olivine, then you fall into the range of a pyroxenite. And I showed you a picture of a pyroxenite last week. This is the way we classify igneous rocks. You identify the mineral content and the percentages, and then you go to a diagram and you plot what its name going to be. Now, this one contains all olivine. We're way up here at the tip of the diagram. That means this one is a dunite. So yes, it's a peridotite. A dunite is a type of peridotite containing greater than 90% olivine. This one falls in the Harzburgite range because, yes, it also contains all olivine, right, and orthopyroxene, no clinopyroxene. So we fall over here. So this is a Harzburgite named after the Harzburg Mountains. Okay, so anyway, a little preview of rock classification. Again, something else you will be doing when you are in petrology. All right, now, so if you have a rock composed of olivine, it's going to be granular, and then you'll see single grains in basalt, and these grains tend to be euhedral because the olivine grows first, right, in this cooling magma, so it usually doesn't run into anything. So over here I show you several phenocrysts, right? Here's a basalt, you can see the vesicles, and inside there, this is a kind of an abnormally large olivine crystal, but typically the phenocrysts, you know, are more or less euhedral. Now, you grab your hand lens, and these are very easy to see because the rock tends to be black or dark gray, and the grains tend to be green. Really nice. The pyroxenes are harder to see. Here's the green sand beach, right? And you take up a handful, and of course it's all full of green minerals, little chunks of basalt. There's some little pieces of coral in there as well. But you can see all these little beat up sand grains. They're all well rounded, and they don't beat up too easily, right? Because they don't have a lot of cleavage, and they're hard. So they're kind of like when you see quartz sand, you know, it gets all rounded and it's smooth and it's nice. Okay, so now optically, quartz is, olivine is orthorhombic, right? We said that it's biaxial. Then it's got a high 2V, and the higher you get the FO content, the higher the 2V gets. So if you get up into the FO 70, 80 range, you're going to get almost a 2V of 90 degrees. And if you go over 90 degrees, then you go back from, that's why it can be both positive and negative, because once the 2V gets to a certain point, then it becomes the other, right? You go from being positive to negative. Very high birefringence, okay? So you're going to see highly birefringent grains. In plain light, they're going to be very high relief. Remember, the relief is based on the difference between the N value of the mineral and the N value of what it's mounted in. And the mounting medium is about 1.540. These are up there around 1.7, so it's going to be super high relief. They're colorless, okay? Even though olivine has that green color, they're colorless in thin section. Now, this is showing you cross polars. If you saw a single grain, because it's orthorhombic, you should see parallel extinction. Now, this is a plutonic rock. This is a peridotite, likely a dunite. And you can see that once you get to know your metamorphic rocks, that these have these what we call polygonal grain boundaries, where these grains all ran into each other growing. And see the cracks in here? There's no real, the straight lines that you're seeing, those aren't cleavages, those are grain boundaries where these grains ran into each other. Think of like when you grow soap bubbles inside a container, they smash into each other, okay? But inside any one grain, the grains are cracked. So you're going to see a colorless, high relief, cracked grains, and that is a dead giveaway for olivine. Put in the analyzer, you see a high birefringence. Okay, there's a range of birefringence here because there's a range of views. But you're also, when you put in and you take a figure and you get this sort of spinning isogyre, and you go, wow, that's like an optic axis figure with a really high 2V, dead giveaway for olivine. Now, in a volcanic rock, here's some phenocrysts, some very large phenocrysts. There's the ground mass. Those are all little plagioclase feldspar laths, along with some iron oxides, maybe some glass, maybe some clinopyroxene grains. But this is olivine. You see this sort of diamond shaped like that. And it's very euhedral. Again, all cracked. That's second to third order colors. This is the same slide in plain light. And again, you'll be able to zoom in and see that it's got very high relief and it is colorless. Olivine. Now, a dead giveaway in volcanic rocks for olivine also is this alteration to a mineral called Eddingsite. And Eddingsite is a weathering product like a clay, and it's got iron in it. So what you see is this sort of staining. It looks like it's been stained red or sort of rusted red. And that is a material. It'll be all in these cracks and all around the edges. And again, that's Eddingsite, and Eddingsite only affects the olivine. Eddings was a famous petrologist, and so they named this after him. What else? Oh, the mineral you're going to confuse olivine with the most would be the clinopyroxene diopside. Diopside and olivine form together in gabbros. They may be in basalts together, right? But again, the big difference is going to be is diopside has good cleavage, right? It's a clinopyroxene. Olivine, not so much. Okay, moving on to garnet. Now look at that garnet formula. Yikes. Okay, but again, don't freak out. It just means that different cations can occupy the different sites, right? They're going to be these different octahedral sites. And again, there's our dead giveaway of our SiO4. Well, it's been increased to Si3O12, been multiplied by 3, but that's okay. Don't let it worry you. And garnets don't really give anybody a problem because they're easy to identify. They tend to grow well. They're metamorphic mineral, right? So we see them like the Wrangell garnets sticking out from the rocks, these little brown lumps. We see them in granites. They're pretty easy to identify, equant shaped. And they're always going to grow when you have any kind of aluminum-rich source rock. And so when you metamorphose clays and you get things like muscovite. Remember we talked about how those sheet silicates need the clays. Well, you're also going to get garnet because it's got aluminum in it. Now, what else can I tell you? It's also got fracture, no good cleavage, right? They tend to be euhedral to subhedral when you see them. So a lot of times you're seeing garnets in metamorphic rocks. They tend to be sort of equally shaped. Now, I put this in here because most of the uses of garnet is for sandpaper or abrasives or something to do with that kind of thing. And it says here that 35% of the garnet production in America is used for water jet cutting. So it's some sort of, this is something like a high jet stream of water, and they put a little garnet in there, and it allows them to cut through steel. Abrasive blasting, like sand blasting, but your sand is garnet sand. They can filter water through it. Abrasive powders for, again, polishing and sanding. A nice mineral when it comes to the scope, because of course it's isotropic. And here you can see this is some sort of schist, and all of these brightly colored grains are going to be muscovite in there. So it's muscovite with a garnet stuck in it, which is typical. And in plain light, the garnets have very high relief, right? Because they're very dense, so they have that good high refractive index, and it's going to be far from the mounting glue. Some of them tend to have what's called sieve structure, and if you know what a sieve is, right, it's something with holes in it that the water would pour through, leaving behind like a colander if you were draining pasta. Okay, well, this grain over here, you see this is a garnet, and inside it has lots of inclusions like holes. They're not really holes. Most of that is quartz. And when a garnet is growing, the reaction that creates the garnet actually gives off silica as a byproduct. And so that silica gets trapped in there. So they're not bubbles, but you could think of them like bubbles. Anyway, we call that sieve structure. This one shows it, this one shows it, this one shows it. Okay? And over here you can see this is going to be muscovite mica, colorless, moderate relief. The garnet has super high relief. More muscovite in here. Yeah. Nice, right? What else can I tell you? Okay, dodecahedral shape. Many colors, depending upon the composition of the garnets, they can come in a lot of colors. Now, I threw this in for those of you in structural geology because garnets have a neat use in structural geology. Now, I'm sure you guys have talked about mylanites, and this is a rock, right? This is not a photomicrograph. You can see the coin here. And in a myelinite, if you'll remember, is a rock that has been ground down due to mechanical sort of grinding, right? So instead of like a fault zone being in one plane, think of the whole rock being ground down. So like when you throw coffee beans in a grinder and you hit the button, right, it turns big things into small grains. Well, that's what's happened here. This is all mechanically ground down to a very fine grain size, and that's what a myelinite is. Well, when you zoom in on this with the microscope, and you'll notice that somebody has paid attention and they have documented the directions that they took the sample out of the rock. Because when you look at this, you may not be, what we're trying to figure out is which way did this rock get sheared? And here's a garnet, okay, this is in plain light, and what you see around it is going to be some potassium feldspar and some muscovite. But this is the garnet, okay? If you were to put the analyzer in, the garnet would turn black. And this garnet has been rolled, okay? It's got a concentric sort of a spiral pattern inside it. So when the garnet first started to grow, it was much smaller, and these white grains, which are probably quartz or feldspar, were parallel to the foliation in this metamorphic rock. But as the shearing went on, the garnet got rolled. Think of it like a marble between your two palms. If you sheared your palms, right, the marble would roll. Well, the marble not only rolled, but grew, because garnets love stress. I mean, other minerals are giving up and leaving, while the garnet's going, ooh, you know, give me more, because it likes, that's why garnets grow in metamorphic rocks, right? They like that pressure. So we use the garnet as an indicator of shearing to tell us which way the shear went in this rock. So if you know your petrology and you like structural geology, then you want to go work in some of these mechanically deformed rocks, myelinites and things like that, and you use these like you would offset layers in a fault zone to tell which way went, you know, which way. So anyway, a neat use of garnets. Not only would you name this rock as a metamorphic rock somehow, but you would also use these minerals as kinematic indicators, right? Direction. Pretty neat. I love this stuff, as you can tell. Okay, so let's take a look at some of the garnet varieties. We have pyrope, which is this sort of deep red to black. And you can see the compositions here. It's got magnesium and aluminum, right? The aluminum's important. Again, you're not going to grow garnets unless you have a source of aluminum. And in a metamorphic rock, that means you needed to have clays to start with. Okay? Almandine, that's iron and aluminum. Those are deep reddish brown. And spessartine, these are brownish red to black. That's manganese and aluminum. Grossular, this is sort of a light color, this yellow green to brown, right? That's calcium and aluminum. Andradite, this is a green to brown to black mess, right? No aluminum in that one, but calcium and iron. And then uvarovite, which is a really deep green, beautiful emerald green garnet that has calcium and chrome. So again, garnets come in lots of colors. They form in lots of different environments because they can substitute all these different elements. But hey, they're all isotropic, and they're easy to identify. Okay, the mineral sphene, and some people know this mineral as titanite. And same thing, sphene or titanite. And the reason is it contains titanium. It is the ore or the source of titanium for, you know, if you find a rock with a lot of sphene or a lot of sphene built up in sands, right, this is where we mine titanium ore from. And this is a very common mineral, and it's small, but it's very common in plutonic rocks, felsic plutonic rocks. It's monoclinic, okay? It tends to be fractured, doesn't tend to have good cleavage. This is the actual crystal shape, okay, this diamond. Very high relief, again, like all of these, because their refractive index is far from the mounting mediums. And the thing about sphene, and I'll tell you the same thing about zircon, is it's got such high birefringence, way up there, that when you put in the gypsum plate, it's not going to look any different. That gypsum plate only shifts, right, the birefringent color by 550, and that's just tickling this thing. It's got a large birefringence that 550 doesn't really affect it much. So you're looking inside a granite, and again, here you can see in plain light the sphene, very high relief. Here's some biotite, okay, pleochroic biotite. You can see the bird's eye texture here and the different birefringent colors. This is going to be potassium feldspar. There's some perthite there, and then here's a chunk of sphene. Well, when you put in the gypsum plate, that potassium feldspar is going to change dramatically to blue or yellow. This isn't going to change at all. So that gives you sphene, and that shape, that diamond-like shape like that, is really, really common. Okay, and they're colorless to pale brown, and they're biaxially positive, but you're really never going to get a figure on one because they're typically too small. Zircon, all right, zircons are tetragonal, okay, so they're actually uniaxial positive, but again, they're so small that you're never going to get a figure on one, but okay. Anyway, extremely high relief once again, and extremely high birefringence. So once again, when you think you have a zircon and you put in the gypsum plate, it's not going to change. It's just going to look the same under there. All right. Now, you can mix up sphene and zircon often if the grains were eroded and you really couldn't see what the shapes are. Zircons tend to be this sort of capsule shape, whereas the sphenes tend to be more wedge shaped. But they're very common as single grains. They're small. Now, they also are found, I told you this before, when you look in biotite for especially. Here's a biotite grain in plain light, and remember all those little, what we called the metamict halos. Those are those black scorch spots that, because of the zircon content, has nuked the surrounding crystal structure. So the zircon contains a little bit of thorium. That thorium's radioactive, and it has destroyed the crystal structure around this. Now, the center image here is what's called a cathode luminescence image, so sort of like a X-ray, right, of a zircon. And look at all the concentric growth patterns here. And I told you when we started the lecture that zircons are the oldest dated thing on Earth, right? And they're really amazing. They're incredibly resistant to erosion. They're hard, they're dense, they're small. And so what happens is a zircon grows in a granite, right? It crystallizes in a granite. That granite weathers and falls apart and turns into mud and sand and anything else. Okay. That zircon goes into the sand, turns into a sandstone. That sandstone gets buried, metamorphosed, melted, and the zircon doesn't melt. You add a new rim around it. So basically, the zircon is, you pull it out of there and you'll see a cover on it from the youngest rock, and down here in the center, it may be an older rock that grew it. So you'll have these rings, like tree rings, that you can date in the zircon, telling you the history. And some of these zircons have the most fantastic histories. Think about them as like the black box on an airplane, right? It survives the crash. And so when you understand zircons, you can trace back the history. Not only can you date, not all of them are really old, right? So you can use the zircons, fishing tracks, the little trails and tracks that are left from these radioactive elements inside them to tell how old rocks are. But the oldest rock on Earth is 3.96 billion, but they've got zircon crystals in Australia that date back, what, 4.2, 4.3 billion, almost back to the age of the Earth. Man, that's fantastic. So if you ever want to come back, if you're getting reincarnated, if you get reincarnated as zircon, you're going to last a while. Okay, cool, right? They're little turds in granites and things and in felsic igneous rocks, but you know, they're important if you want to date rocks or look at rocks past histories. All right, moving on to the aluminosilicates. The aluminosilicates are the group of minerals called, well, they're Andalusite, named after the Andalusia region of southern Spain, where the Andalusian horses come from, Kyanite, and Sillimanite. And that's not Sillimanite, but Sillimanite. Okay, and all three of them have the formula Al2SiO5. And these are polymorphs, remember? And a polymorph is multiple minerals, same chemical formula. Another polymorph would be diamond and graphite for the formula carbon. Okay, and these are very important, very diagnostic minerals in metamorphic rocks. So here we can see another phase diagram. This is pressure on the y-axis, temperature on the x-axis, and you can see the rough areas where these minerals form. So if we are at higher temperatures, lower pressures, we get Andalusite. Okay? If we get higher pressures, we get kyanite, and if we have very high pressures and temperatures, we get sillimanite. Okay? So these, the occurrence of these minerals in metamorphic rocks tells metamorphic petrologists the conditions that that rock formed under. So here's more or less the geothermal gradient, which is about 25 degrees centigrade per kilometer of depth. So if you're growing Andalusite, you're cooler than the geothermal gradient, yeah? And let's see, what else can I tell you? Oh, let's say you found a rock that has both sillimanite and Andalusite in it. That means that your temperature and pressure of formation must be along this line, because that's where those two minerals are stable with each other. If you found all three together, that is the holy grail for metamorphism, and that would tell you that your temperature of formation was about 530 and your pressure was somewhere about 3.2, 3.3 kilobars. Again, all of this will be you'll be exposed to in metamorphic petrology, but very interesting minerals, very easy to identify, very unique, so, and very important. So Andalusite, this is going to be found in the lowest grade metamorphic rocks, the coolest ones, the lowest pressures. Okay, it's orthorhombic like many of our nesosilicates. It tends to have good fractures, not real good cleavage. It has moderate to high relief when we look at it in, you know, plain light. It's got a very large 2V, and remember, if you have a large 2V, it means that your axes, X, Y, and Z, are all about equal to each other. Remember, if one axis is really close to another and the other one's far away, we're going to have a very small 2V. Okay, and they have parallel extinction because it's orthorhombic. It says that they make elongate prisms with a square cross section. So, you know, like something that's tetragonal, like a cube of butter, would be an elongate prism with a square cross section. Now, it's not exactly square because it's orthorhombic, but here you can see when you cut it perpendicular to the elongate prism and you get a cross section that's square. This one version of Andalusite shows this, what's called the Maltese cross, which is sort of the iron cross, right? That's very unique. But typically here's what your sort of cross section looks like. Here's a stubby prism over here. These tend to be colorless to pale pink, right? They don't have very high birefringence. And so if you have a metamorphic rock and it's something in there that's not feldspar, it's not quartz, then chances are it's Andalusite. Okay, kyanite. Kyanite's very distinctive. All right, it's typically found in very high pressure, right, metamorphic rocks. It's triclinic. It's of course, that means it's biaxial. It's negative. It's fractured. It does have some decent cleavage, It's got a very large 2V also, and it's got inclined extinction. Low birefringence, so here it is in polarized light, cross-polar light, so the birefringence is not extreme. It's got, it does have perfect 100 cleavage, so if you happen to get a view, it tends to break these little splintery fragments along that 100 cleavage. In hand specimen, it's very easy to identify. It's got this nice bladed habit, and it's blue, okay? Although it's colorless, here it is colorless with that high relief in thin section. And kyanite has another strange property that it's got different hardnesses in different directions. So if you scratch it one way, it's harder than if you scratch it in the other. So kyanite, another unique, important metamorphic mineral found in high pressure metamorphic rocks. And then finally, sillimanite, the final aluminosilicate, it forms in the highest temperature metamorphic rocks. It's orthorhombic, fractured, high relief, large 2V, parallel extinction, but what separates it from the other aluminosilicates, it tends to have this bladed habit, these really slender prismatic crystals, so they're narrower and longer, splintery looking, yeah? And it's got a moderate birefringence, not as low as the others, so you can see that moderate birefringence here, which is sort of mid-second, high second order, okay? So there is sillimanite. All of them with the same chemical formula. Now, another metamorphic mineral that will be typically found in schists along with the aluminosilicates is this mineral starlight. Now, starlight has a little bit more, because again, it's found with those because it has aluminum, but it's an iron-bearing mineral, and it's also got some O or OH in here. And it's found in medium-grade aluminum-rich metamorphic rocks, which is why you find it. If you find a bunch of muscovite, okay, then chances are you're going to get some starlight. It's monoclinic, okay, it's positive. Again, not great cleavage, but fractured, okay, high relief. It's got a very large 2V and parallel extinction. Now, the thing that makes it very unique in the microscope is, and this is in plain light, is that you'll see this sort of honey yellow to brown pleochroism. And this is very strong. There's really nothing else with this color, all right? And when you put the analyzer in, it's only got first order interference colors. And then like the garnet, remember the sieve texture, okay? So this is all sieve textured. These are all inclusions like blobs or bubbles inside of it. And it's got this kind of wild radiating pattern because starlight tends to grow around other minerals. Now in hand specimen, you get something called a penetration twin, and that's where one twin sort of pierces the other like that. And it's dark and reddish brown. So this is very distinctive in hand specimen. This is really distinctive under the microscope. Now, you may not see these in mineralogy, although they'll be in some samples of schists that we've got. But next semester for sure, right, you'll see this stuff. Moving on to the final mineral is topaz. And topaz, again, a mineral that we've all talked about when we say Mohs hardness scale. It's got the hardness of 8. Nice hard mineral like most of these. Topaz is found in felsic igneous rocks, whether it's volcanic like a rhyolite or a granite or pegmatites, that kind of thing. And you can also find topaz because it's got fluorine and water in here in high temp hydrothermal. So what happens is you get in volcanic terrains where you have high temperature hydrothermal vents, you might get topaz crystals forming in some geode type things, and that's where this guy came from. And that's when you can start to make some gem quality topaz. It's orthorhombic, positive, moderate relief, right? Moderate 2V, parallel extinction. It's got low first order birefringence, okay? So if you look in here, that's grays, first order gray, you know, in there. You might want to confuse this with quartz, but much higher relief and it's got cleavage, yeah. And the 001, that's a basal cleavage. And remember, I talked about basal cleavage before. That's lifesavers. A tube of lifesavers has basal cleavage, right? They pop apart and they let the lifesavers lie on the stage, the ring version, yeah? And they're colorless and thin section. We don't see a lot of topaz, but just in case, if you went to work somewhere and you were working in felsic igneous rocks, topaz would be something that you may want to watch out for. Another nesosilicate. So, the list, last week's list with this week's list added. So there we go. There's garnet, all right, and sphene. Titanite, dead giveaway because of the titanium. Zircon, dead giveaway because of the zirconium. Andalusite, kyanite, sillimanite. Topaz, that fluorine in there helps, and then starlight. Well, you know what this means. And that's it. Okay, so now what I want you to do is you got a quiz this week. That's quiz 6. Gives you some more examples of the types of questions I'm going to ask. It's not the questions I'm going to ask, but they could be similar. And you'll get that done this week, and then the only thing left will be that third exam. And you're going to do great because you guys you always do well on stuff like this. And anyway, have a great week. I'll talk to you later.